going to review a little bit from yesterday. This is where we ended yesterday. And we talked about x-intercepts. X-intercepts occur where y equals 0. Y-intercepts occur where x equals 0. And so in the diagram, there's an example of a y-intercept. Notice graphs can have multiple x-intercepts, multiple y-intercepts. Can somebody think of what a graph would look like that would have multiple y-intercepts?
Squiggly like that.
So,
It would be like an S, a legit S.
like that, is that what you're meaning by squiggle?
Yeah.
I know you meant more squiggles, but that would be, remember we talked about that one, this was where x equals y squared. So that would be one where you have multiple y-intercepts. Very rarely do you have multiple y-intercepts. Generally, you will just have one. And you will have some instances of none. Okay, you looked at, yesterday, in your domain and range problems, you actually had one that looked like this. It looked like this right here. And this is one in which there is no y-intercept. Likewise, there is no x-intercept because it doesn't touch the x or y. So you will not always have an x and y-intercept. So let's just go ahead and look at this. It says use the graph of the function f of x equals x squared minus 4x plus 4 to approximate its y-intercept. Then find the y-intercept algebraically. So in looking at that, the y-intercept is where it crosses the y-axis. What does the y-intercept look like in this problem? 4. So now what we're going to do is confirm it algebraically. Y-intercept occurs when what equals 0? X. So all you're going to do here is plug in 0 for x. 0 squared minus 4 times 0 plus 4. When I have the zeros, remember those are gone. So your answer is 4. There you go. That's it. Let's look at the next one. Use the graph of the function to approximate its y-intercept. Then find the y-intercept algebraically. So what's the estimation here for the y-intercept? -1. Then what I'm going to do is go ahead and plug in 0 for x. So if I plug in 0 here, I get the absolute value of 2, which is 2 minus 3 gives you -1. So there you go. Think you can handle that?
Whoa, yeah.
Okay, let's look at the next one. All right, what's the y-intercept look like here?
2.
2. Once again, I'm going to plug in what for x?
2.
0.
You always plug in 0.
So 0, yep, to the 4th, minus 3 times 0 squared plus 2. So what's your answer going to be here? 2.
I like this.
So far, so good?
Yeah,
Now this one actually has 2 x-intercepts too.
it's true.
All right, to approximate its zeros. 0 is another name for x-intercept.
Oh.
So basically when it says to approximate its zeros, they mean to find its x-intercepts.
Why don't they just say that?
Because they try to make it complicated.
Because when we look at some word problems and some story problems and we talk about finding the functions of the zeros, that it fits better in the word problem. You don't just say find no x-intercepts. So they were getting you to know terminology that's going to help you solve problems. So x-intercepts. Looks like how many do I have? 3. And what are the 3?
-1, 1, and 0.
-1, 0, and +1. So now it says find the zeros algebraically. So to find x-intercepts, what do you let equal 0?
1.
Y. So here, this is going to be 0 equals x cubed minus x. So I need to solve that. What do I notice about both of these terms? They both have a what? X. So I'm going to factor that x out. So when I take that x out, what am I left with? X squared minus 1. So now, while we're on the factoring mood, let's just go ahead and x squared minus 1 is the difference of 2 squares. What will that factor to be? X plus 1, x minus 1. And so my 3 solutions are 0 right here, -1, +1. So 0, 1, -1. They in fact match. So let's look at it again. Another one. Use the graph of that to approximate its zeros. Find its zeros algebraically.
Five.
Estimate that it is 5.
What?
Five.
Say about
4 and a half,
maybe.
5. Go with 5.
So obviously, you look, it's gonna be going right here. So somewhere, you think somewhere between 4 and 5. So you, like some of you said 4.5. Let's see. So now to find its zero algebraically, I'm gonna plug 0 in for f of x, or y. So 0 equals root x plus 4 minus 3. So how do you solve that first? Move the 3 over, because in order to undo a square root, what do you have to do?
Square it by
You have to
itself.
square both sides, and so you have to get it by itself, which is exactly right. And so now, by adding 3, what do you do now to solve that equation? Square. So on the left I get 9, on the right what do you get?
X squared plus
X plus 4. Because remember the squared and the square just cancel, and so what does x equal? X equals 5.
I knew it. I said 5.
Okay, isn't that neat how it works?
Hey Mason.
All right, let's look at this one. Okay, we're going to talk about symmetry now. Okay, symmetry. This is in your book. These are the tests for symmetry. First of all, a graph is symmetric with respect to the x-axis. If. Okay, so basically it's symmetric to the x-axis if there's a mirror image over the x-axis. So if you look at this, it's mirrored over the x. That's all you have to remember. If it's symmetric with respect to the x, it's mirrored. Now there is a test, and that is to replace y with negative y. So to determine if it's x-axis symmetry, you replace y with negative y. Y-axis symmetry, on the next one, means that it's the mirror image at y, folds on itself. This one, you replace x with x. And then last but not least, symmetric with respect to the origin basically means if I were to fold along the x-axis and then fold along the y-axis, I will get the graph. So it's kind of like the diagonal one. So the best way to do this and figure out if it's symmetric with respect to the origin, if I fold this along the x, would you agree that this is what I'm going to get if I fold it along the x? Okay? Then now what I'm going to do, because I folded it on the x, so that basically means flipping it this way. Now if I fold it on the y, this now goes over here. And this orange now goes over here. So it has folded on itself. So that's how origin symmetry works. You fold it on the x, fold it on the y. This one you have to replace both. And this isn't going to make a whole lot of sense till we look at an example. So let's look at this. It says use the graph of the equation to test for symmetry with respect to the x, the y, and the origin. Okay. Support the answer numerically, then confirm algebraically. So in looking at this, what does it look like it's symmetric with respect to? The y-axis. Now for those of you wondering, how did you get y? If you were to take this graph and you fold it along the y-axis, it folds on itself. Okay? It's the mirror image. So now you need to go ahead and support it algebraically. So if it's y-axis symmetry, remember, y-axis symmetry, we replace x with negative x. Okay? So y equals, so in place of x, I'm now going to put negative x. There we go. Squared plus 2. What happens when you square a negative? It becomes a positive. And so really, that becomes x squared plus 2. That's exactly what I started with. That is how you confirmed it algebraically. That's all you have to do. You have to do the replacement and then show that the function is exactly the same as when you started. That's how you prove that it does in fact have y-axis symmetry. Let's look at another one. Use the graph xy to test for symmetry with respect to the x-axis, the y-axis, and the origin. First of all, does it look like x-axis? Y-axis? Origin? Possibly. Okay, it looks like it because it looks like if we flip it and flip it, it's going to flip on itself. So we're going to kind of do a little test. So remember to do origin symmetry. I replaced x with negative x, and I replaced y with what? Negative y. So I start with xy equals negative 6. So in its place, I'm now going to put negative x, and in y's place, I'm going to put negative y. Well, what happens when you multiply negative times negative? That becomes positive, so you get xy equal -6, which is exactly where you started, which means it has origin symmetry.
Very nice.
So pretty much anytime there's two different lines, it won't be X or Y. Because
Depends, but yeah. I mean, that's a good thought. Okay, next thing we're going to talk about are even and odd functions, and this is the last thing. A function that is symmetric with respect to the y-axis is called even. So if it's got y-axis symmetry, we call it even. If it's got origin symmetry, we call it odd. If it's got x-axis symmetry, we don't call it anything. Okay? So in looking at this,
Why
we need
axis
to,
is in
y-axis is even, origin is odd. So notice what it says. It says graph the function using a graphing calculator. Analyze the graph to determine whether the function is even, odd, or neither. Confirm algebraically. If even or odd, describe the symmetry of the graph of the function. So, does that have y-axis symmetry? No. Does that have origin symmetry? No. So this is actually neither. There you go. Okay, now we will go over how to graph those shortly. Okay, I'm going to get through these examples and then we'll go. Let's look at this one. What symmetry does this have? Okay, it has y-axis symmetry, which makes it even. So if it's even, it's got y-axis symmetry. So remember y-axis symmetry, what do we need to do? What do we need to replace? X with negative x. So y equals negative x squared minus 4. Up, you know, negative times a negative is positive. There you've confirmed it algebraically, you're good to go. So it's just like going one step beyond what we did. You're just going to say whether it's even or odd. We got one more to look at, I believe. Okay, this one.
Odd.
X has negative.
are we ignoring the
Yeah.
graph and have to be different?
Yeah, because we're going to talk about that later.
No, it's
Origin.
even because.
So has it got y-axis symmetry?
No.
Okay, it doesn't have x-axis symmetry. Origin symmetry. Okay, let's see. If I were to fold this over on the y-axis, it's going to look something like that is going to be on the y. Over here, that, and then something like that. Now, if I fold along the x, is that going to fold along itself? No. So this one is neither. Now, the way you could, for those of you saying, oops, gotta spell it right. For those of you saying origin, all you would have had to do then is plug in x and negative y, and you would have found it didn't work. The main reason it doesn't work is because of the x squared here. All right, let's go ahead and look at your assignment then, pages 19 through 20. 2 through 44, the evens is what I gave yesterday. I want you to go ahead and open that up. We're going to go ahead and look at some individual questions. Okay.